Hello, it's Keith here, and this is lesson 4 of my 6809 assembly programming tutorials. Today we're going to be discussing the stacks, and I said stacks because the 6809 has 2 of them. Now, if you don't know what a stack is, I will discuss it for you, and I'll just briefly describe it. A stack is basically a temporary store. Now, if you think of our 6809, we've only really got the A, B, X and Y registers. Now, we do have the direct page for storing things, but often there may be times where we need to just store something for just a few moments, maybe a few calculations, and then get it back again. Maybe we need A and B to do some mathematics, but then we need the original values of A and B back in A and B later on. And that's what a stack does for us. The stack you can think of kind of like an in-tray in your office. You might have a nice big in-tray and you might have lots of paperwork. People give you papers and you can't deal with them at the moment, so you put them into your in-tray. Now, if you think of your in-tray as a thing you can put things onto the top of, but you can only take the top item off the in-tray, so your jobs are sort of building up and you're always taking the most recent one you received off the top when you come back to do one of the jobs, that would be accurately describe the way the stack works. It's known as a last in, first out stack. Last in, the last item in the stack is the first one taken out, and that's the way the stack works, and you'll see how that works when we come to looking at the code and the examples. Now, the stack works using a piece of memory. There's a pointer to the end of the stack, and every time we add an item to the stack, the pointer moves down the memory, and every time we take an item off, the pointer moves back up the memory, and hopefully it ends up at the same place it started, at the top of the stack memory. Okay, so that's the concept. The 6809 has 2 stacks. The S stack, which is the main stack, and the U stack, which is known as the user stack. And actually you can pretty much use that for whatever you want. You could use it as a sort of temporary variable. You can use it as a pointer to some memory. You can use it like effectively like another X and Y register. But of course you can also use it as a stack. So we're going to be looking at it today, and we're going to learn how all of these stacks work on the 6809. Okay, well, let's go over to the code and let's have a look. Okay, so this is the lesson 4 example code. We've got 4 examples we're going to be looking at today, and these will work hopefully on the FM7 and the Dragon. Now, because we're messing with stacks, and as we'll learn later, the stacks are actually very important to the sort of fundamental workings of the processor. We are having to actually sort of trick things, and we've got some hard-coded memory addresses here that are going to be good for these systems. So if one day in the future you're running it on a different system, you'd need to give it valid memory addresses. And we've also got some code that's going to actually dump the contents of the stack, and that's why we need the stack in a fixed memory location so that we can see the contents nice and clearly. Okay, so let's have a look at the first example. We've got 4, and they just discuss various concepts of the stack, and hopefully I will be able to explain them to you. Okay, so here's stack test 1. Now, the 6809 has a variety of commands for working with the stack. These are known as push and pull effectively on the 6809, very much like the 6502. They were push and pop on the Z80. Now, here we've got the push to the S stack command, and you can see we're pushing the D register, which is a combination of A and B. Now, the opposite of that, taking an item off the stack, is the pulls command, pull off the S stack. We also have a push U command and a pull U command. So that's for the S stack here, push S and pull S, and push U and pull U are for the U stack. So we've got 2 different options there. Now you can see here we're specifying a single D register, but we can actually specify multiple registers on the 6809. The 6809 has quite a few clever tricks up its sleeve. So we can specify multiple registers. Here you can see we're using the D register, but we can actually use A and B as well. We do have the options. We're going to see all of those options in a moment. Okay, so here's our example code, and let's look at what we're doing and let's discuss each line. Now, I've put tab indents in my code here, and I've tried to represent what's happening with the stack. If we don't take everything off the stack that we pushed on, we're going to end up in a mess, and we'll find out why later on. So I tend to find putting tabs every time I push onto the stack and then moving back every time I take things off keeps things neat and helps stop me making a mess of things. So hopefully it'll help you as well. So first of all, what we've done is we've loaded FEDC onto the D register, and we've pushed that onto the S stack. Then we've loaded 1, 2, 3, 4, and we've pushed that onto the S stack. Now what we've done is we've loaded another test value, FFEE, into D, and we've pushed that onto the U stack. Remember, there's 2 stacks, the main S stack and the user stack. Then we've loaded DDCE, and we've pushed that onto the U stack again. And then what we've done is we've used this monitor stacks function, and this will show the two stacks to the screen, and you can see those stacks being shown to the screen here. Now we've set the S stack to the 3E00 range here, and because that's the starting address and the stack moves down, we're actually seeing the address just before that, and this is the user stack here, and that's the second one just here. Okay, so let's see what actually happened. So we first loaded that FEDC and we pushed that onto the S stack, and you can see that right at the top of the S stack here. And basically this is configured to show the very end of the stack on the right hand side here, which is the starting address, because remember the stack goes down as we write. So FEDC was pushed onto the stack, you can see it there. The second item comes before, because remember it's moving down memory. So here 1, 2, 3, 4 has been loaded in just here. That's the S stack. You'll notice the rest of the data is garbage, we don't recognize it, and that's because the other data was pushed onto the user stack. So FFEE was pushed onto the second user stack here, so that's that address value here, and then we pushed on DDCC, and you can see that value just there. So we've pushed items onto the two stacks, and we can see them represented in memory here. Now what we've done is we've pulled off the stack, but we haven't just pulled off one item here, we've pulled off X and we've pulled off Y. So we're loading two registers in one go, and we're then going to show the contents of the registers just here. So here is the starting point before we did our second set of pulls. So you can see that X and Y just contain two random values here, and you can see that the S and the U stack have these values here. Now what we've done next is we've pulled two registers off the stack X and Y, and these have then been loaded back into X and Y off these values in the stack. Now we then did another push onto the stack, so you can see that the stack registers haven't actually changed here. But if I just modify this code just a moment, I think we can make it a little bit clearer. If I put an extra dump here, well, now you can see that when we pulled those two items, those two 16-bit items off the stack here, the stack pointer went up by 4 here. This user stack has gone up by 4, so you can see that when we take the items off the stack pointer goes back up, and you can see that now these two values have been restored. But then what we did is we pushed them back onto the stack, and we showed the contents of all the registers again. So here the stack has gone back down by those two items by 32 bits there, by 4 bytes there. So you can see we're back down to 3CFC here. Now what we did next was just something to make a point. I've pushed X and Y onto the stack here, but I've pulled Y and X off the stack. Now you might assume that that's going to make a difference. You know, if we push item X onto the stack and then push item Y onto the stack, and then we pulled Y off into the X register, you might think that would swap them over. But when you put a list of items in a single command here, it actually, the command doesn't look at the order you represented them. It works in a fixed order each time, and that's quite handy for us later on. We'll learn why there's a big benefit to that. So the list that the order that we put them in here doesn't make a difference, but if we put them as separate commands, then it would. So let's put, for example, pull Y and then pull X here. Now if I run this here, you can see that X and Y have now been swapped around. X now contains the previous Y value and Y contains the previous X value. But if I put them the other way around, well, you can see now that the order hasn't changed. The point I'm making is if the pull commands are in a single line, the order doesn't matter. But if the pull commands are separate, then the items are pulled off the stack, but it doesn't matter what register was pushed on. It will be pulled off into whatever register we specify. And you can see this again down here. We've pushed D onto the stack here twice, but then we pull them back into X and Y off the main stack here. So you can see the 1, 2, 3, 4 FEDC here. Well, first we pulled the X register, so the X register took 1, 2, 3, 4 here. And then we pulled again into the Y register, and that took the FEDC value just here. So as I say, pushing onto the stack, it doesn't matter what register we push on, the register that we pull off will take the value even if it's not it's not the same register. And actually it doesn't even matter if it's the same size. I will show you what I mean by that. So if we, instead of pulling D off or pulling Y off, if we pull A off, A is an 8-bit register. So in this case, we've now pulled off the A register, and we've still got that FEDC on the stack here. So we've pulled A off and we've got FE here, and then we've pulled A off again and we've got DC here. The point I'm making is we can push on a 16-bit value and pull off 2 8-bit values as well if we want to. As I say, I mean, generally speaking, I'd suggest you try and keep everything as simple as possible, but there's going to be times you may want to do this, so it's definitely worth knowing about. So that's the basics of the stack. Now let's have another look at using different sizes of registers, and also we're going to look at how we can get things back to the original state, resetting the stack without pulling everything off it. As I say, it is important that we take everything off the stack that we put on. We will see why in a future example, but for now just take it that we do need to do that. It's important that we keep everything tidy. So here in this example, we're actually pushing a stack pointer onto the stack. We can do things like this. We can push everything onto the stack, as you'll see in a moment. So we're pushing the S stack register onto the U stack here, and you can see that's been represented just here. And then what we're doing is we're loading some test values into A, and we're pushing them all onto the stack. So you can see here that we've pushed FF, EE, DD and CC onto the stack. We then show the contents of the stack, which is what you can see here with this monitor StackS command. And then we're pulling the X register off, and this is what I just showed you a moment ago. We can load 8-bit registers onto the stack and then pull a 16-bit register off the stack, and that works just fine. You see here we've loaded X off the stack and we've got CCDD here. Now if you look at the value of the stack position here, you can see that this has gone from 3DFC to 3DFE. Now at this point we have not taken everything off the stack that we put on. We've still got another 2 values onto the stack. Now if I want to make sure my code has the same stack position at the end as the start, one option would be to pull another 16-bit value off the stack, but actually what I've done here is I've simply pulled the value of the stack pointer off the stack, and of course you could store it in a temporary memory address or register as well. I'm just using the point that we can push a stack register onto the stack. In this case I'm pushing the S stack onto the user stack here, and that has restored the stack pointer, even though we've never actually pulled that final item off the stack. You know, maybe our code has branches and one of those branches doesn't need those items again, and in this case I've managed to get rid of those items just by pulling the value off the stack, although we could equally just add value to the stack, or as I say, restore it from somewhere else. So there we go. So that's another example of how we can put items onto the stack in an 8-bit form and then take them off in a 16-bit form in a different register. And of course that's all perfectly valid. The stack really doesn't care how we use the data on it. It's just got these commands that we can use however we want, which is very much true of all of the things within the 8-bit processors. We have a lot of flexibility, and sometimes that means we can do a lot of damage. So that's the risk we take. Okay, so now we're going to look at this extra example, and this is where it comes into why I said that it's so important we make sure we undo everything we did to the stack during our little programs. And this is because the main stack, the S stack, is used during subroutines. Okay, well let's take a look here. So what does this example do? Well, it loads FF onto the stack, it loads it into A and then pushes that onto the stack. We're then just doing a monitor. I'll just indent that, that'll be a bit clearer. And then we're jumping to subtest. Subtest is loading another value onto the stack, EE, just pushing that on there, and then it's showing the monitor, then it's loading another value onto the stack, and it's showing a monitor again, and then it's showing the total state of the stack. Then it's pulling those items off the stack and it's returning. And so of course execution will continue here, and we'll pull those items off the stack as well. Now let's take a look at the stack and let's see what happened. So first we pushed FF onto the stack. Well, you can see FF just here, so that makes sense. Now, our subroutine pushed EE onto the stack, and we can see EE just here. But we can see another value here. Well, what's that? Well, what that is that's the return address of the subroutine. You see the subroutines, the jump to subroutine command uses the S stack. What it does is, whenever we call a subroutine, the return address is pushed onto the stack, and whenever we do a return from subroutine, the return address is pulled off the stack. So that is the return address, and that's why our next push of EE went here. Now we did do another subroutine call just here, but that subroutine will have returned by the time our code continues, so the return address will have, it would have disappeared, but actually it stays there, it just gets overwritten. So you can see here that DD is then the next one because the stack has been restored because of that return. We then push onto the stack. So here we're able to see the full state of the stack here. And then what we're doing is we're pulling a value off the stack and we get the first one DD here, and we're showing that to the screen, and you can see that just here. Then we're pulling another one off the stack, we get this EE. We then return, we then show the stack again. You can see that the DD and the EE have vanished. Now this isn't actually a function of the stack, the values would have stayed there, the stack pointer just moves, but these testing routines are actually corrupting the data beyond the end of the stack pointer, so they're getting removed by that. It's not a function of the stack itself, but you can see here now that the FF is still here, and then we are pulling that off the stack as well and showing that to the screen. You can see that just here, and then we're finished. So this is an example of a subroutine that uses the stack, and as I say, in this case we've taken all the items off the stack that we put on, and that means that when we come to do our return command we get the correct address and return. However, if we didn't clear the stack up in some way, either by restoring it in some fashion like we did up here, or just popping everything off the stack, then when we try and return, we're not going to get the return address. For example, if I do this, I've now left one of my accumulators on the stack, and you can see that the code is actually locked up. We've not got the final results here, whereas if I put it back on, well, now you can see we've got all of the values here. So by not pulling all of the items off the stack, we were breaking our code, and really when we do that, anything could happen. It's quite possible we'll jump to a random address within the program ROM or something. The screen could clear, the devices could go crazy, the disk could start whirring, and anything could happen. You really don't want to do it, and it's one of the most common causes of crazy crashes in your code. You know, things have gone totally AWOL. The reason is you've run a random piece of code and literally anything could happen. So you need to make sure your stack is in the same position at the end of your routines as the start, and that's why, as I say, I do these tabs so that it's less likely I'm going to make a mistake, especially with the 6809, where you can push two 8-bit values on and pull one 16-bit value off, and everything's back to the way it was. Okay, so that's the third example, and that's why the stack is so important, and it's so important we need to make sure that we don't mess it up. Now what we're going to do this time is another subroutine test, and this time we're going to push and pull multiple items in one go. Now the point I'm making here is that we can really push anything onto the stack. As I said before, we can push stack pointers onto the stack, but in this case we're pushing the condition codes, the flags, and we're also pulling the program counter off the stack. Now the program counter is the current running address. Well, what does this do? Well, let's have a look at our code and let's see what happens. Okay, so we've loaded 1, 2, 3, 4, 5, 6, 7, 8, and we've loaded a 0 here, and then we've shown the monitor here, and you can see those values here. Then we've jumped to our subtest. We've pushed all of those items onto the stack. We've loaded FFEE DDCC, and we've shown those registers, and you can see them here, FFEE DDCC. And then we've shown the stack, and you can see here on the stack 1, 2, 3, 4, 5, 6, 7, 8, and I guess the condition codes are here. Now that's what we've pushed onto the stack here. What about this value just here? Well, as I said before, when we do a subroutine, the return address is being pushed onto the stack. Now you can see here we've got a pull command, and we're pulling the program counter off the stack, and there's no return. Well, because the jump to subroutine pushes the return address onto the stack, and the program counter is the current running address, if we pull the program counter off, we'll actually get that return address, and it's effectively the same as having a return command, but we've built it into our pull command here, so we've saved a little bit of memory. So by doing that, we're saving a command, and that's going to help us out a little bit. Now again, as I said before, it doesn't matter what order we put the commands for pushes and pulls. When they're all in a single line like this, the command will actually run in an automatic order, because the assembler is compiling this to a command that doesn't have an order that's represented by the text here. So the order is sort of hard-coded, and it's quite handily hard-coded so that the program counter is the last item that's pulled off the stack. So even if we put program counter in the middle here, it's actually going to pull it off as the last item, and it's going to automatically return for us. As I say, this is something that is really quite remarkable. It's something that the 6809 has, that you see it on systems like the ARM, but this was really quite impressive to me to see you could do this. So anyway, I thought that was something quite impressive, and it's definitely something you want to take advantage of because it will save you a byte of your code. No return command, so that's definitely something you want to try and take advantage of because it's something quite unique to this system really. So there we go. So those are the examples we're looking at here. So this is how we can push items onto the stack with push S, push U, and pull S and pull U. But of course, we can also use the other addressing modes to read items on the stack without affecting the stack pointer. If you look at the addressing modes, we can use the S and U stack pointers as indexes, and we can use offsets to those if we want to read items on the stack without affecting the stack. But today's examples was about discussing using the stack as a temporary store and how it affects subroutines. So that's beyond what we want to look at today. Anyway, that's all we're going to cover today. As always, I'd suggest you have a go with the code yourself. You can go and get it from my website, give it a go, try things out. You're going to find you'll probably cause crashes with the stack. Everyone does, so don't worry about it. But it's something obviously you need to know about. And the 6809 I find much more... I really find it a lot easier than the 6502. The registers are so much more powerful, and the stack allows so much flexibility. I was always relying on the 0 page a lot with the 6502. With the 6809, I hardly need it. So I really quite remarkable for me. I really enjoy 6809. Anyway, I hope you'll enjoy 6809 too. If you do, please like and subscribe because there's lots more coming. I'm working on keyboard graphics and sound tutorials for all of the 6809 systems I cover. That's the FM7, the Dragon and the Vectrex. So if you want to see that, hopefully you'll stick around. If you like the video, YouTube might think it should recommend it to other people as well. That's apparently how the YouTube algorithm works. So please like if you did like the video, and please subscribe if you want to see more, because the number of subscribers really encourages me to keep working on the videos, and it takes an awful lot of time and it's quite stressful. Anyway, I hope you enjoyed this. I hope you'll enjoy your 6809 programming. Thanks for watching today, and goodbye.